Alright, so like chapter 10, chapter 11 rehashes some linear things in a rotational sense, but this chapter brings in a couple of sort of new things that we definitely want to talk about. The name of this chapter, Rolling, Torque, and Angular Momentum, and you can see the main concepts are split up amongst those three topics, although I reversed torque and angular momentum just so that when I define torque as the derivative of angular momentum, you've already seen it here. So, rolling motion. Rolling happens a lot in our world, and we can explain it with some relatively simple expressions. I'm going to talk about how when there's no slipping, then the velocity, the linear velocity at the radius of, say, a wheel equals the velocity of the center of mass, and that's rotationally speaking, as I'll explain in more detail later. When dealing with conservation of energy type problems, we have to consider two types of kinetic energy. That's rotational kinetic energy and linear kinetic energy. So the total rolling kinetic energy is going to be the sum of these two. And you can imagine gravitational potential energy turning into kinetic energy. That's going to affect how fast something is moving, because some of the gravitational potential energy has to go into rotational. Anyway, more on that later. I'm going to derive this. This is sort of a complicated expression, but the linear acceleration of something rolling down a ramp follows this. And as you know from ramp problems in the past, dealing with net force equations, the component of gravity down the ramp is Fg sine theta or mg sine theta. So typically the acceleration of something just sliding down a ramp would be g sine theta. But when you have rolling involved, you have this little extra doohickey on the bottom, which I'll derive. Again, notice that it just becomes a equals g sine theta when the denominator equals 0. So when there's no rolling, then there's no icom, no radius, all that good stuff. So this becomes 0, and it's just g sine theta divided by 1, which is g sine theta. I'll also talk about a yo-yo and how it's really just a specific case of something rolling down a ramp, and that's a ramp of 90 degrees. Then we move on to angular momentum, which is just like linear momentum. Linear momentum was mass times velocity. In this case, angular momentum is rotational mass times rotational velocity, or moment of inertia times angular velocity. But we can also express it as a cross product of r cross the momentum, the linear momentum. Very similar to torque, which I introduced in the last unit, last chapter. You can expand momentum to be mass times velocity, but the mass is not changing, or the mass is constant, so you basically pull that out and this becomes r cross v with this extra mass term. In dealing with angular momentum, we need to use the right hand rule, and I'll show you how k is positive k is pointing towards you and negative k is pointing away from you. And we still have conservation of momentum, in this case conservation of angular momentum. And finally, torque, which I talked about in chapter 10, I just want to expand a little bit, and we deal with the relationship between torque and angular momentum. Basically the same relationship as there existed between force and linear momentum. Remember that force was the derivative of momentum with respect to time, and so torque is also the derivative of angular momentum with respect to time. And continuing along the lines of linear to rotational relationships, if work, when we had a constant force, if work equaled force times displacement, then rotationally work will equal torque times angular displacement. So that's the summary. Let me go into detail on the first main concept. So, rolling motion. this first one, when there's no slipping, vcom equals v radius, let's focus on these two pictures here. As you can see, we have a wheel here, and the velocity of the center of mass you can measure at the center of the wheel, because that's the center of mass. And point P is always directly below the center. And what you do is you roll the wheel, right? And we started here on the wheel, but as we roll, this point on the wheel rolls up along the arc length. And so the length of this arc length is the same as this flat part on the ground, right? And so you can see that if the center of mass covered this distance from here to here, so did this arc length. And so that's essentially why the velocity of the radius, of a point on the radius, which is like a point right here at P, equals the velocity of center of mass. You can see that down here for pure rotation. Velocity at a point on the radius v equals velocity of center of mass. Also the case for translation, which is moving left and right, or just moving from one place to another. So you got pure rotation where you're not moving around, you're just rotating. You got pure translation where you're not rotating. Notice the difference though at the bottom. Because of the way you're rotating here, the direction of the velocities change direction. They're opposite directions, 180 degrees opposite of each other. And so when you add the two together vectorially into rolling motion, you get vcom and vcom twice, so you get two vcoms. Here you get nothing and vcom as just vcom, and here negative vcom and positive vcom cancel out. So this is just what you would see if you're looking on the side. Actually, there's a picture I can show you real quick. Alright, here's a picture. So this is like someone riding a bike, and they took sort of a longish exposure so that you could see some of the motion in the picture. And notice it's blurry up here, and it's clear here, representing the fact that this would be moving faster than this, right? And so that's basically giving you a visual of the sum of the vectors for rolling motion. You're moving fast up here, twice the center of mass velocity. That's why it's more blurry up here than it even is in the middle. And there's no motion down here, so it's nice and crystal clear. We stopped here, so that's a nice little visual to show you that. I'll just leave this picture here. I don't need to do any writing. Yep. Alright, so the other thing we want to talk about for rolling now, we've done problems in the past where a block has slid down a ramp. So that was just linear motion, or as they say here, translational motion. Just no rotating, just sliding down. But when you're rolling down, you have both translational and rolling motion. And so when we're doing conservation of energy problems, then we want to consider both the rotational kinetic energy, which is don't forget 1/2 I omega squared, in addition to the 1/2 mv squared, which is the translational or linear kinetic energy. And you can imagine that if some of the energy is going into rotation, that means less of it will go into linear, and so the speed will be less. So you can probably imagine who's going to win in this race. The sliding one's going to win because all of the kinetic energy, all of the potential energy is going into linear kinetic energy, which in turn is the speed that it ends up with down here. Yeah, anyway. Let me just finish off this video with I'm not going to be able to derive this in 5 minutes, so I'm going to stop this video here and do this next. I don't want to rush it. Do this in the next video. Alright, see you soon.